Welcome to a lesson on determining the potential function for a conservative vector field. The reason that determining a potential function is very useful is based upon the fundamental theorem of line integrals. This theorem states that if the vector field f is conservative, then the line integral between any 2 points is the difference in values of the potential function little f, as we see here, at the 2 points regardless of the path. So this theorem can simplify the process for evaluating a line integral if we know the vector field is conservative and if we can determine the potential function. So remember, if f is a conservative vector field, then the components are the partial derivatives of f with respects to x, y, and z, as we see here. So to determine the potential function to help us evaluate that line integral, we'll have to integrate each partial derivative with respects to x, y, and z, as we see here, and then we'll compare the results to determine the potential function f. So let's go ahead and give it a try. Again, we're already given that this is a conservative vector field. I do have another video that shows how to test for a conservative vector field. But since we know this is conservative, we know that the partial derivative of f with respect to x is going to be equal to 3x plus 2y, and then partial derivative of f with respect to y would be equal to 2x minus 3y. And so the potential function would be the original function f of x, y. So if we integrate 3x plus 2y with respect to x, we should recover the x part of the original function. And if we integrate 2x minus 3y with respect to y, we should recover the y part of the original function. So let's go ahead and give it a try. Here we'd have 3 times x squared over 2, or 3 halves x squared, plus 2xy, plus, now our constant of integration could be a function in terms of y because we're only recovering the x part of the original function. So we'll let the constant of integration be c of y. Now let's go ahead and integrate 2x minus 3y with respect to y. So we'd have 2xy. Here we'd have minus 3 times y squared over 2, or 3 halves y squared. And in this integral, we're only recovering the y part of the original function, so our constant of integration could be a function of x. Now that we've recovered both the x and the y part of the original function, we want to compare these two antiderivatives to determine what the actual function would be. So f of x, y must contain the term 3 halves x squared. It must also contain the term 2xy. Notice this term does occur in both antiderivatives. And looking at our second antiderivative, we also have a y squared term that we have to include. So we'll have minus 3 halves y squared. And we still could be missing a constant, so we'll call it plus c. This would be our potential function that we would use to evaluate a line integral if we knew the vector field was conservative. As we know from Calc 1, we could leave off the constant because that would be eliminated. Let's go and take a look at a second example. Here we have a three-dimensional vector field, and since we're told that it is conservative, we know the partial derivative of f with respect to x would be z squared plus 2xy. The partial derivative of f with respect to y would be x squared plus 2. And the partial derivative of f with respect to z would be 2xz minus 1. And now we'll need to set up 3 integrals to recover the x, y, and z parts of the potential function. So we'll first have the integral of z squared plus 2xy with respect to x. And then we'll have the integral of x squared plus 2 with respect to y. And then lastly, we'll have the integral of 2xz minus 1 with respects to z. So we'll find all 3 of these antiderivatives and then make sure the potential function has all of the possible terms. Integrating with respects to x, we'll have xz squared. Integrating 2xy with respects to x, that'll give us 2 times x squared over 2 times y. So the 2's would simplify out. We'd have x squared y plus Our constant of integration can be a function in terms of y and z. So we'll call it c of yz. Integrating with respect to y here, we'll have x squared y plus 2y. And then our constant of integration can be a function in terms of x and z. Integrating with respect to z here, we're going to have 2x times z squared over 2, or xz squared minus z plus a function in terms of x and y. So our potential function f of x, y, z must contain all of the terms we see here. We just have to watch out for any duplication. Let's go ahead and start with x squared y. I see an x squared y term here and here. So that term must be part of the original function. Here we have an xz squared term, and there's another one here. Let's include that term. And we must also include 2y minus z. And then of course our constant of integration, we'll just call that c. And again, the significance of this is if we know the vector field is conservative, then the line integral between any 2 points is the difference in values of the potential function, which we just found, at these 2 points regardless of the path. So the potential function can make evaluating a line integral in this case much simpler. I hope you found this helpful. Thank you for watching.